Greetings to you all. Good people, we will be doing a bouncing ball. Now, when the ball hits the ground, what happens is the ground exerts an upward force on the ball for a short period of time. This is larger than the downward gravitational force. Therefore, there is an upward net resultant force. Okay. So what we are saying is when the ball hits the ground, when it is in contact, the ground will be doing what? Applying an upward force that is greater than what? That is greater than the gravitational force. So the ball will eventually move in an upward direction because the net resultant force is directed upward. So the harder the ball, the shorter the contact time with the ground. And that will mean the larger the upward force. Where is this coming from? This comes from F net is equal to what? Is equal to the change in momentum over change in time. If the contact time is short, this is inverse proportionality. Okay, so if the contact time is less, that will mean the force will be greater. So for harder balls, the contact time is short, so the ground will apply a greater force on that ball, and the ball will move upward with a greater velocity. Okay, so sometimes the contact force is being ignored, okay, or is taken as being equal to 0. So we'll be doing an example where the contact time is ignored. Okay, now example 1, a ball is dropped from a building which is 50 meters high. The ball reaches a height of 8 meters after the first bounce. Okay, so what happens is, let's say this is going to be our building. Now the ball is dropped. The building is 50 meters high. From there to here, it's 50 meters. So the ball is being dropped. Okay, it is moving in this direction. Okay, now this ball it bounces. As it reaches it bounces, boom, and it reaches a height of what? A height of 8 meters as it bounces. Okay, should have used this red pen. It bounces and reaches the height of what? Of 8 meters after the first bounce. Okay, so we are asked to calculate the velocity of the ball just before it hits the ground, the velocity here. Okay, now before we calculate the initial velocity, there's something that I want to explain. Why is it that the ball only reaches 8 meters above and not reach the 50, that height from which it was dropped? It is because here, as it is in contact with the ground, some of the kinetic energy is converted into other forms of energy, such as heat, and also the deformation of as the ball deforms when it is in contact with and also sound energy. Okay, and if possible, they can also be light energy. Okay, so since we lost some of the energy, now into other forms, no, not lost, energy cannot be lost, but can be transferred into other forms. So since some of the energy is being converted into other forms of energy, so the kinetic energy that is left, that will be converted to the gravitational potential energy, will be minimal. Hence it only reaches 8 meters after the first bounce. Okay, so the contact with the surface is going to be inelastic. It is inelastic here. It is inelastic. Okay, now we are asked to do what? The velocity of just before it hits the ground. Now let us do A here. A. Okay, now before we start to attempt questions with vertical projectile motions, we must indicate the directions. So I'm going to take upward to be positive and take downward to be negative. Okay, so with my data, collecting my data, okay, now the ball was dropped. So if it is dropped, the initial velocity is equal to 0 meters per second. Okay, now it is that, and also I know that the gravitational acceleration is always directed downward, so that will be negative 9.8 meters per second squared. And I also have what? I also have the displacement. Now if we take what to call the position of the ball, we always take it as what? As the zero reference point. So if this is the zero reference point, 0 meters, now the ball will be taking a negative direction. It will be covering a negative displacement, okay, because it's going down. We took down to be negative, so this is going to be negative 50 meters. We are looking for what? We are looking for VF, the velocity at which it is there, it is the ground. So that will be what? That will be we're going to say this is going to be VF squared is equal to VI squared plus 2G changing y. Okay, so VF squared is going to be equal to, that will be 0 squared plus 2 into negative 9.8 into negative 50. Okay, so our answer there is going to be 0 squared plus 2 into negative 9.8 into negative 50. Now we have 980. So this 980 is equal to VF squared, square root on this side, square root on this cancels that. VF is going to be equal to plus or minus the square root of what? This is going to plus or minus 31.30 meters per second. Okay, so that velocity, because we are taking the negative one because it is pointing, it is directed downward, so that will be VF is 31.30 meters per second downward. Okay, good. Now let us do what? Let us do B, the time it takes to reach the ground. B, the time it takes to reach the ground. So I'm going to use this formula. VF is equal to VI plus G changing time. So the final velocity is negative 31.30. So that will be negative 31.30 is equal to, it was dropped, that will be 0 plus negative 9.8 changing time. Negative 31.30 is equal to negative 9.8 changing time. We divide both sides by negative 9.8. This cancels that. So the changing time is going to be equal to, now the changing time is going to be what? That will be negative 31.30 divided by negative 9.8. The answer will be 3.19 seconds. 3.19 seconds. Okay, good. Now for C, we are asked to calculate the velocity at which it leaves the ground after the first bounce. Okay, now when the ball bounces, for the first time, when the ball bounces for the first time there, now the first projectile, we can take it as we are having two projectile, two separate projectile motions. The first one is this one, when the ball is dropped and it hits the ground. So since it is in contact with the ground, it is no longer in free fall, because now we've got the force that is applied by the floor on the ball, and we also have the gravitational force. There are two forces involved here, so we are no longer in free fall. That will be the end of the first projectile motion. So we are taking that we've got what? This is the start of the second projectile motion. Okay, so whatever that we got on this one, it has nothing to do with the second projectile motion. And also, we cannot assume that the velocity at which it leaves the ground, it hits the ground, is the same as the velocity at which it leaves the ground. Why? Because some of the energy here, like I have explained, it was converted or transferred into other forms of energy. So the velocity at which it leaves the ground will not be the same as the velocity at which it first hit the ground. So we will have to find the initial velocity separately, because we know that it reaches what? The height of what? Of 8 meters, and we know there the v is what? Is 0 meters per second. This is the maximum height it reached after the first bounce. Okay, and it is covering what? It is covering what? A positive displacement, if we are taking this to be the initial point. So this is going to be our 0 reference point for the second projectile motion. So for C, I would say let me collect my data for C. That will be VI. That's what we are looking for. We've got VF, which is equal to 0 meters per second, simply because it is what? This is going to be the initial velocity, this is going to be the final velocity, and we know at the maximum height the velocity is 0. And we have G, which is negative 9.8 meters per second squared. And we are going to have what? We are going to have the change in Y, which is what? Positive 8 meters. Why positive? Because now this is the second projectile motion, the second one. Okay, so this will be the start of what? This will be the start of the ball. So where the ball starts, that is our 0 reference. So from here, where it starts, it goes up. Now it is covering what? It is covering a positive displacement. Now we take upward to be positive. We are taking upward to be positive. So now we can find what? We can find VI. How can we find VI? We can simply use the formula VF squared is equal to VI squared plus 2G change in Y. Okay, so what is the final value? That will be 0 squared is equal to, we're looking for this, VI squared plus 2 into negative 9.8 times 8. Okay, times 8. And now what are we going to have there? We're going to have 2 times negative 9.8 times 8. The answer will be negative. We're going to have 0 is equal to VI squared minus 156.8. We transpose this to the other side. What are we going to get? We're going to get 156.8 is equal to VI squared. Okay, so we are looking for VI. So what do? We introduce the square root on both sides. This cancels that, and then plus or minus. Okay, so VI is going to equal to plus or minus times negative 1. The square root of answer is going to be 12.52 meters per second. So this is going to be VI. because the correct one is going to be this one. The negative one is going to be the right one. This is going to be 12,52 meters per second downward. Okay, good. Now also since we are still there on C, we've got what? We've got D. On D, we are asked to calculate the time it takes to reach what to call the 8-meter distance after the first bounce. Okay, now we can calculate what? We can calculate the time after the first bounce. Okay, let us say that will be our D. Okay, because here we have what? We've got our data there. We can calculate D. Okay, now how do we get D? We can use this simple formula. VF is equal to VI plus G changing T. VF is how much? It's 0. That would be 0 is equal to we now have the no, sorry for that. This was not supposed to be downward. This was supposed to be upward. Sorry for that mistake, simply because this ball is going up, so this positive one is the correct one. Okay, it's not going down because the ball is going up. This initial velocity is the velocity of it that is going up, so that will be 12,52 plus negative 9,8 changing time. Okay, now we transpose this to the other side. We're going to have 9,8 changing time is equal to 12,52. We divide both sides by 9,8. We divide both sides by 9,8. This cancels that. Now the changing time is going to be equal to answer divided by 9,8. The answer is 1,28 seconds. So the time it took to move from here to there is 1,28 seconds. Okay, now let us come to E now. We're going to do E on a separate on a clean page. Now, so I wanted to collect or to call all the information that is required for us to draw the graph. Okay, because we have to draw. Okay, so with E we're asked to draw the velocity time graph for the entire motion, So what I'm going to do is I'm going to have points. Okay, now the first point here is going to be A. This is going to be A. That will be a point A. I'm going to have A there, and then here I'm going to have B. Okay, B. Okay, I'm also going to have, let's say, C. C is the velocity at which it leaves the ground, and then we are also going to have D there. Okay, okay, up until it reaches what? For the entire motion, 8 meters. Okay, so now let us come to drawing what? To drawing our our graphs. Now at A, for what? For the velocity, time graph. At A, what is the time at A when the ball was dropped? The initial time was 0. Okay, what is the velocity here at A when the ball is dropped? The velocity there is also 0. Okay, this is time against what? Against velocity. Time is independent and velocity is dependent. So I'm going to have another point which is B, when it hits the ground. So what is the time when it hits the ground there? That is 3,19 seconds. That will be 3,19. Now what is the velocity at B there? The velocity at which it hits the ground, that is negative 31,30. Negative 31,30. Okay, now C, for C. Okay, C. Now what is the time when it leaves the ground? So in this case we are ignoring the contact time, so we are saying it leaves the ground at the same time when the ball reaches the ground. Okay, so you're gonna see at that time it's still 3,19 seconds, but what is the velocity of the ball at that time when it leaves the ground? Now it left the ground at positive 12,52 meters per second. It is 12,52. Okay, because they said for the entire motion. And then at D there, the maximum height. Okay, what is the time at that point? So the time will be this time. Okay, that will be this time, because this 3,19, it is this time from there to here, plus 1,28 seconds that it's gonna be this time and that time. Okay, so that will be 3,19 plus 1,28. So the time now here is 4,47 seconds. At D the time is what? At D the time is 4,47 seconds. And what is the velocity at the time? The velocity at that time is 0. Now how do we draw this? Okay, so we're gonna say okay, now we're going to use our ruler. Okay, where is the pencil? And then we say so if this is my 0, and then I'm going to use no. So this one is going to be my 0, and then with the time I'm just going to have just going to have 1 2 3 4 5. 1 2 3 4 5. Okay, 1 2 3 4 5. So this is going to be say 5 10 15 negative 5 negative 10 negative 15 negative 20 negative 25 negative 30 negative 35. This is going to be 1 2 3 4 5. This will be what? This is going to be time in seconds. Okay, this one is going to be the velocity in what? In meters per second. These are the units for velocity. Now, simple. Since we've got now the times and the velocities, the first point is going to be here, 0 and 0. After 3,19 seconds, 3,19 seconds, if this is 3,5, 3,19 is going to be somewhere there. It's going to be somewhere there, and then we just use our ruler going down like this. We go straight to negative 31, negative 31, negative 31 is somewhere there, comma 30. This is going to be our second point, and we join the two like that. Okay, now we go to what? To C. At the very same time, at this time is the time it bounced. Okay, so we go to what? To that what to call velocity there, which is 12,52, and then if this is what to call 10, 12,5 is in between there, and then this is going to be our third point there for C. So you must remember that what to call at this point the contact time is being ignored. Okay, now at what? At 4,47 seconds, 4,5 is somewhere here, 4,47 is somewhere there. The velocity, so the final velocity is 0. So we just do what to call join the 2 points. Okay, just join the 2 points like this, like this. Okay, good. So but if it was said that this ball it bounced for the second time, plot the velocity time graph until the second bounce here. So that will mean our graph will come to negative 12, will come to negative 12,5, because the velocity at which it leaves the ground is equal to the velocity at which it will leave it will hit the ground again that side, but it will be in the opposite direction. Hence you will extend this graph toward to negative 12,5. But for now we have to end here at the maximum height, where the velocity is equal to 0. Okay, so this was what? That was E. That was E. We also have what? We also have F. Draw the displacement time graph for the entire motion. Draw the acceleration time graph for the entire motion as well. So for the displacement time graph, we will also need to do the same as we did with the velocity time graph. Okay, we need to have these points. Okay, since now we know the times, okay, there's going to be A into, we know the times is 0. We just need to find what the displacement there, and then B, what is the time at B is 3,19 seconds, and then at what to call, we need what? We need the displacement at this side, and then at C, what is the time at C? The time at C is still 3,19 seconds. We need what? We need the displacement at the time. Now at D, what is the time? The time is 4,47. We need to find what? We need to find the displacement. Okay, now let us come to find the displacements there. So at A, the displacement, if we take A as the what? As the zero reference point, so the time there is 0. Now what is the displacement at that point? The displacement there is equal to 0. That will be 0. At B here at this point, what is the displacement? The displacement is negative 50, because the ball covered a negative displacement. Now still at C, when it leaves the ground, it's still there at the ground, the displacement is still negative what? Negative 50. Okay, now it is going up. Okay, it is going up. At D, that will be what? The displacement will be from here to there. So how do we get this displacement? This is going to be negative 50 plus 8, because now it was going up. Okay, now that will be negative 40, negative 42. Okay, negative 42. Now let us try to do what? To draw the velocity time graph, the displacement time graph. This is going to be the displacement time graph. Okay, so we have up until 250, and then here we have so we're going to need 10 of these. We're going to say if this is our 0, do 1 2 3 4 5 6 7 8 9 10. Okay, 1 2 3 4 5 6 7 8 9. So this is going to be my 0. The times are still going to be the same: 1 2 3 4 5. Okay, this is going to be what? 5, negative 5, negative 10, 15, 20, 25, 30, 35, 40, 45, 45, 50, negative, 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 and we say this is displacement in what? In units of meters, and this is time in seconds. So that will be 1 2 3 4 4 5. Okay, so at 0 and 0 the displacement is still 0 there. Now at 3,19, if this is going to be 2,5, 3,19, it's somewhere there, and then we take that downward to what? To negative 50. Okay, we have a point there, and now C and also C and B are the same. The point is still there. At D, at 4,47, 4,5 somewhere there, and then 4,47 just adjacent to 4,5, and then we take it down there to what? To negative 42. Okay, 42 is going to be somewhere here. Okay, now the displacement time graph is parabolic, so we are going to have a curve like this, and then like that. Okay, then like that. So you don't have to have so many lines, only one line. Okay, only one line. Good, like that. But if had the ball bounce for the second time, okay, and then we have to plot until there. This was going to come here again to the -2 to -50 there. It was going to come like that, okay, after some time. Good. Now let's come to do the last one, G. Okay, this one's F. This was F. Now let us come to do a G. With G, let's draw the acceleration time graph for the entire motion. Okay. Now with G, what do we have with G? Okay, I'm going to cut this page like this, and we're going to write G here. Okay, now with G, we're just going to have the times. We'll have to start good. And then let's say this is going to be 5, 10, 15. Let us just end it there, and then we're gonna have 5 there. 5, 0, 5, 10, 15, negative. Okay, and then this is 1, 2, 3, 4, 5. So with the acceleration time graph, time graph. Okay, now how is this one different? Now at this time here, which is what? Which is flip. At this time here, 3 comma flip. Okay, this was not supposed to be here. It didn't bounce here. It didn't bounce there. It didn't bounce there. Okay, so this is going to be, this is where it bounced at 3,19 somewhere here, and then go down there, straight there to what? -50. Bounces there, and now it comes to negative at that time. So it's gonna curve like that to this point until it gets there. But that's how it's supposed to look like. So this is where it bounces at this time. Okay, so we know that our gravitational acceleration is 9,8. We know that G is equal to -9,8 meters per second squared if we take upward to be positive. So -9,8 is going to be somewhere there. We're going to draw a straight line until we get to this time of what? Of 3,19, when it started to bounce. Okay, at 3,19, that is the point where it started to bounce. So we are going, because at that point it is not only the gravitational force that is acting, also the force that is applied by the ground. Okay, so there is a net resultant force, okay, that's acting there. So we're going to have it like this, and then what happens is we're going to, it's gonna end at 4,4,47, which is somewhere there. So at this point, this is the time, the contact time when it was in contact with the floor, because there was what, there was a net resultant force which we changed the acceleration to what, to be positive, because the ball there was change of direction. It was going down and then it accelerated upward. Okay, as soon as what you call gravity was the only force acting. Now when it went up, as soon as gravity was the only force acting, now the gravitational acceleration was back to what, was back to 9,8. Okay, good. Now let us now do example 2. Okay, with example 2, okay, we are now considering what? We are now considering the contact time. What do we have? A ball is dropped from which is 50 meters high. The ball reaches a height of 8 meters after the first bounce. The ball is in contact with the floor for 0,31 seconds. Calculate the velocity of the ball just before it hits the ground. So guys, we have already calculated everything, because this is the same example as this one. Okay, now the velocity at which it hits the ground, that will be what? That will be Vf is equal to that will be negative 31,30 meters per second. Okay, we calculated it here. Now B, the time it takes to reach the ground, that is that time. That time is what? Is 3,19 seconds. The velocity at which it leaves the ground after the first bounce, we managed to get that here. That is positive 12,52 meters per second. Because now I want us to do what? I want us to understand how are we going to plot our graphs when there is contact time. Okay, so we don't have to recalculate these things because we already have them here. The time it takes to reach the 8-meter distance after the first bounce, it took 1,28 seconds. So that will be what, 1,28 seconds. Okay, now draw the velocity time graph for the entire motion. Okay, now we are now considering the contact time. Now how are we going to plot that? Now let me draw the first one here. The velocity versus what? Versus time. The velocity versus time. Okay, I don't think we are going to have sufficient space. The space is not going to be enough. Now the space is not going to be enough. Let us use this one. I will draw it there. This is going to be the velocity versus time. Okay, and then we're gonna say and then I'm going to have 1, 2, 3, 4, 5, 6. Because it has to be straight as this point. This is going to, so that we have enough equal equal spaces in between. So that will be 1 2 3 4 5 6. Now what do we have now? We've got time in seconds, 1 2 3 4 5 6, and then we're going to have 5 10 15 20 25 30 35. Okay, all these are negative, 5 10 15. Okay, now I'm gonna write velocity in meters per second. Now how do we go about this one? It is the same as this one. Okay, it is the same. The only difference is going to be what? Is going to be the contact time. Now let us have our points here. Going to have A. What is the time at A? The time at A was 0 and the velocity was also 0. At B, when it reached the ground, okay, when it first hit the ground, okay, when it first hit the ground here, the time is what? 3,19 seconds. The time is 3,1919. Okay, but what is the velocity at which it is the ground? The velocity at which it is the ground, that is negative 31,30. Now we come to what? We come to C. Now what is happening is this ball is dropped there, and for some time there is a contact time which is equal to 0,31 second. Okay, now it reached the ground after 3,19 seconds. So we are going to have what? We are going to have A, B, and then there is some time there. The ball is still on the ground for 0,31 second. We are going to have C, and then now it does what? It leaves the ground. So it means the time at C is going to be that 3,19 seconds plus the contact time. So that will be what? That is going to be 3,19 plus 0,31 seconds. So that is 3,5. We are now going to have at C 3,5. Okay, 3,5. But the velocity at which it leaves the ground is still 12.52. Okay, now D. There at D, what is the time? The time after the first bounce, the time it took for this motion it is what? It is 1,28. Okay, so we need to add this 1,28 from that 3,5. That will plus 1,28. That is going to be 4,78, and the velocity there is 0, simply because this is the maximum height. Okay, so now we've got all the information that is needed to plot the graph. Now let us start. Now we're going to have 0 and 0 is there, 3,19 it's somewhere there, and negative 31 is somewhere there, and then we're gonna have something like this. Okay, and then 3,19 is okay. We plot there. Okay, and then what do we have at C? The time is now 3,5. It's somewhere there. 3,5 somewhere there, halfway. Okay, and now the velocity is 12,5 to 12,5, somewhere between 10 and 5, somewhere there. Okay, and 12, and the time of 3,5, somewhere there. Okay, now I hope you are aware of that space, of that time. Okay, that will be the contact time. The difference in these times, that will be the contact time of 0,31. Now this is our what to call the velocity at which it leaves the ground. Now what is the time when it reaches the maximum height for the second time? The time is 4,78. This is 4,5, 4,78. It's somewhere there. And then the velocity is what? It's 0. So this is our point. We join the 2 points. We join the 2 points, and also we join those 2 points. Those 2 points. Okay. And then now, what do we do? And then we can just use the dotted lines here. Just the dotted lines like this. Or you can just leave it as it is. Okay, good. Now let us now do the displacement time graph. Okay, the displacement versus time. When there's what? When we are now considering the contact time. When considering the contact time, it means these are going to be our times, because here we already considered what? The contact time. Okay, so for A, the time is 0. We just need the displacement there. B, the time is 3,19. We need displacement there. And for C, the time is 3,5. We need displacement there. And for D, what is the time? The time is 4,778. Okay, and then we need the displacement there. Okay, now how do we go about this one? We will say, what is the displacement at time 0? The displacement is 0. The displacement is 0 there. Taking this as our 0 reference, the displacement is 0. At B, the displacement is negative 50. Okay. So when at the time when the ball is still in contact with the floor, the displacement, it is still what? It is still there at the bottom, there on the floor. At C, it means it is still what? It is still at negative 50. Okay, and now it goes up and covers a distance of 8 meters. Now the distance is going to be from there to here. The displacement will be 50 minus 8. No. Negative 50 plus 8. That will be negative 42. At this point is negative 42. Now come to our graph, and we say, okay, how do we plot this? When I say, okay, flip, this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2. Then 0 there. Now our times 1, 2, 3, 4, 5, 6, like this. Okay, 5, 5, negative 10, negative 15, negative 20, negative 25, negative 30, negative 35, negative 40, negative 45, negative 50. That, and that is going to be 1, 2, 3, 4, 5, 6. Okay, now we plot our graph. 0 and 0, this is going to be our point there. Okay, the next one is B. What is the time? 3,19 at what? At negative 50. 3,19 somewhere there, negative 50 is there. You just do it like this and you say okay, this is going to be our point there. Okay, now the next point is at 3,5. 3,5 it's somewhere there, halfway there, and then take it down here to what? Still, so what? Still there. Okay, and now the time is 4,78. 4,78 somewhere there, and it is now negative what? Negative 42. Negative 42 somewhere there, and then we can say okay, and with the cross we have what? We have our point there. So the displacement time graph is a parabola. We're going to have our graph like this, and we join these two, and we go like that. Okay, I hope you can notice the difference. Okay, especially with the first one. Okay, with the first one you can see here what to call the contact time was not considered, it was just ignored, but here we are considering what? We are considering the contact time. So this is the contact time with the flow, so it will just end there. Okay, good. Now what to call, even for the what to call acceleration, here we are asked to draw the acceleration time graph. Okay, now for that one we can say, okay, for G you can just draw it here, quickly draw it here. Zero here, and then we say the times 1, 2, 3, 4, 5, 6. Okay, this is going to be 5, 5, 10, 15, negative, negative, negative. This is the time in seconds, and this is going to be the acceleration in meter per second square. So guys, you must also write this side, the dependent variable and the units. Okay, so this is going to be 1, 2, 3, 4, 5. Okay, now from our graphs we have what? We have the times. Okay, so here at 3,19, that is when it is the ground. So you can say, okay, this is going to be our 9,8, this one, the gravitational acceleration. Okay, but here at 3,19, and then it leaves the floor at 3,15. 3,15 it's somewhere here. So we are going to have something like this. Let me just say, okay, we're going to have something like this. We just draw solid lines here, okay, and then from there we're going to have something like this, and then we bring it back like this, and we continue until the end of the motion. The motion ends at 4,78 seconds. That will be 4,78 seconds. It's somewhere there. That will be the end of our motion. That is how we're going to draw the three graphs: the velocity time graph for the entire motion. Considering the time, it will be this one. You can see the contact time there, and also there is a contact time there, and we also have the contact time here, which is 0,3131 seconds. So good people, I hope you understand and you enjoyed this lesson. That will be the end of this lesson. Thank you.